guys. Can you hear me well?
Yes.
Cool. So I'm Angelo. I work with RISC Zero, and I was really trying to figure out a way to be me. So I decided to try to take you on this little journey, right? About love and relationship. Relationships are tough, right? I bet you guys had tough ones. Someone? Tough relationship, no? Definitely good ones, right? Otherwise you would not be smiling right now. A mix. But in general, they are tough, right? I love this quote from Dr. Aaron. I hope I pronunciated him correctly. But it basically comes from this theory of self-expansion and kind of says that when you are in a relationship, you in order to get the most out of it, right, you really need to embrace the resources, the perspective of each other, so that then when you can take challenges together, you get the best out of it, right? And typically this brings to a healthy and long-lasting relationship. So now you will be confused because of what the heck is this? Why are we talking about relationship? Now, I will show you why. So typically relationship start with attraction, typically, right? Not all the time, but sometimes they do. And in the case of blockchain, right? If you think about where blockchain is coming from, you really need to try to, put the blockchain hat, right, or feel the same shoes, right? It was originally designed as a settlement layer. And of course, blockchains evolved over time, right? But, intrinsically, they still have the original challenges. Of course, they get improved, right? But I would claim that still we have some limited execution capacity. And I'm talking about the ability to execute a certain amount of computation. Obviously, depending on the consensus, all the nodes need to compute the same computation over and over until they reach consensus. And so you have it's basically a finite resource, right, to the amount of computation that they can all compute before reaching consensus and advancing the state. And this also brings some of the scalability trade-offs, right? So you have latency, right? You have also hardware requirements. There are blockchains that try to play this game rather than the other game, and also also related to latency and other hardware or networking requirements. You have limitation on the block, and some of the blockchains also have privacy issues. So think about or maybe if I were to be a blockchain, right? And then someone comes around and basically whisper into my ear all my secret desire, everything I always wanted. I kind of feel like, it's like game on, baby, right? So ZK comes and basically, promises this moving the execution of chain to achieve a really high level of scalability. And then it can be done with a very efficient way of verifying the proofs. And they can also be, ZK can also be used to enhance privacy. Then it's like blockchain gets very euphoric, right? It goes into the second stage of a relationship where you basically start dreaming and see the partner as like the perfect match. Like there is nothing that can go wrong. And you stop listening and be objective. I think objective is a really good phase. I think everybody should experience, even if the outcome might be not the one that you expect. In fact, in reality, most of the time, this is what it looks like. Nonetheless, if you really believe in this relationship, you go on, right, and you start the so-called early attachment phase. And this is like one of the phases that I really like, because it's the most natural one where you try to get to know each other a little bit better. You start learning what the other likes, that dislike, the pros and cons. And if you are still really into the relationship, depending on how things evolve, you might eat some prizes. Right? I bet any of us have experienced some prizes during a relationship, right? And in this case, the crisis can come from several aspects. In the case of performance, might be because of proving times are too long, or the proof size is too big. It can take several aspects, right? But if it's it's not just a flint, then you finally get the best, right? The deep attachment phase, and we kind of really believe in this relationship, right? So one way to look at this, to strengthen this we think successful, right, destiny, it's to really do a full stack commitment, right? And boundless is exactly that, right? So we try to hit hard on every layer, right? From the execution in state-of-the-art performance. One of my favorites is the integration, right, with this really cool dev tooling that helps people to really leverage the benefit from each other, right? And then one also important thing that kind of touch to the the self-expansion theory that I discussed at the beginning, which is basically proving. And in the case of ZK, right, I believe personally that it should embrace the ethos, right, of the blockchain, and this decentralization, this openness, right. So even the proving should be such that anybody can basically participate into generating and requesting proofs, right? And also, it shouldn't be a limit to the blockchain, but actually an additional added value, right? And that also is achieved by making the consumption of the proof, right, of the output of this, first of all, cheap, and second of all, usable everywhere. Otherwise, it's kind of pointless, and then you get the crisis. So this is basically a more practical view of what boundless is, right? You can imagine, like, from the lower layer with the verifiable execution. It's currently we have the RISC Zero ZK VM. I don't know how many of you know it or they have used it already. It's pretty cool, pretty fast, and it's always improving. And then we have also planned, of course, to improve its architecture with the 2.0 version, but we also are open to see the adoption of other ZKVM on this layer. And then you go up, and of course you need to have a layer that makes use of these nice proofs, right? So the ability to verify should be everywhere, right? So we deployed a verifier contract in any chain, or well, most of the chains. And then in the middle layer is the one that I recall the decentralization ethos and openness. So basically we envision the proving layer to be decentralized, where everybody can participate as prover, and also everybody can request proofs, right? And there is no central authority, single point of failure that could break this nice game. And then we have the super interesting integration tool. I think we have seen one also in the previous presentation that kind of sits in that more or less like layer from my point of view, which is basically the most important glue, right? To take some of the, or most of the benefit that ZK can bring to any Web3 app in a seamlessly fashion, right? So one example is Zeth, which is a block producer. And then we have also Blockstream Zero, which instead is able to verify the Celestia DA attestation on chain, right? And then we have the basically main topic, right, of the rest of this presentation, which is steel, right? So we are gonna get to steel in a second. And then you have the top layer where you have, the L1s, you have, roll-ups, or you have coprocessor, whatever you want to do, basically. So, talking about steel, or in general, talking about integration tooling, right? One question that I was always fascinated was how can we unlock provable smart contract execution? Basically, I'm asking how can we create a good match between what is already in blockchain and how to make it more viable using ZK. And I'll go a little bit back historically, because I don't know how much you know about how the storage works in Ethereum, and how you could basically at least start getting probably access account and contract storage. But long story short, basically you can imagine, you can think about the storage of a smart contract, right, as a mapping of slots and values. I don't know if you were listening to the previous presentation, he mentioned with the really kind of scary expression about slots. It's not that they are ugly or anything. I like them; they are indexed at the end of the day. But the problem is that it's not that trivial to find them, right? And unless you, I don't know, you like going looking for mushroom or that kind of activity, it's not like the best way to spend your time, right? So of course there are tools to help you with that, but I think we can do better. But in general, the idea to historical way to achieve this will be basically to find this storage slot and then use a really nice method, right, that the EIP 1186 standardized, that is materialized with this ETH get proof, which is basically you give this slot index, and then this method gives you back a sequence, right, a list of hash values basically that you have to hash together to prove that this slot belongs, right, to the state against when selecting some block number, right? Basically, it goes back to the root hash of that state, and then you can perform this verification within a ZK VM or whatever, right? You can generate a proof for this. So this is basically, the long story short of this primitive. Now, this kind of sucks, right? Because, again, from a DevX point of view, it's not ideal. And then, of course, depends on the taste of the person. Maybe there is like a developer that just loves to do that. Super fine. We are all different. But one other question is, can't we just, for instance, query solidity functions? I mean, at the end of the day, we want to know stuff about Ethereum, and the way you interact with Ethereum is, via solidity, right? You write, you read. So, in order to do that, you will need to do what? To prove the execution of a given smart contract function, right? Executing in the EVM. You just need to prove that. And turns out that this is like not easy, I mean, not difficult at all. It's super easy, right? So this is basically what Steel does, right? Using powered by the ZK VM, it allows you to integrate with Solidity. You can literally just write Solidity to query any view call, right? Without learning any new language, maybe a little bit of Rust currently. But in the future, you will not need that. And then one important thing is that you suddenly have unlimited compute. And by that, I mean that since you are executing off-chain, you do not need to rely anymore on the limit of the computation amount, right? That one transaction on one block can hold. That also translates into reducing a shitload of gas, to be French. Right. So, so basically, what a developer can do with this, right? They can use existing smart contract logic, which it's sometimes in the real world is super important because there are companies or applications that they have invested and they have spent so much money, they have audited their code, so they would really love to keep executing that rather than re-implementing the same logic into some other language. Also, you can prove not only the latest state, but also historic date. Yeah, you can basically query historic blocks, right? So to get the state with respect to that block. And you can also, if you want, you can just optimize a subset of your logic, right? With that, right? In general, one thing that I really like about this is that it unlocks materializing and deploying application that otherwise would be just impossible because of the current limitations. And this it's something that makes first of all blockchain happy, but most importantly everybody happy. So how it works? Well, the trick is that if you're not familiar with the ZK VM, how it works, basically you have a guest code, which is basically the code that runs into the ZK VM, and the code that gets basically proven, right? And then you have the host side, which instead is basically the driver that feeds the input and then takes out the result, right, from the execution. And using the host, you can run a phase that we call pre-flight, which basically what it does, it runs the view call for you, and it stores all the information, the storage, all the accounts that have been involved during this call. And for each of that, basically, storage and accounts, it basically retrieves the proof of inclusion via this ETH get proof, so that then once this environment is fed into the guest can actually verify that the entire environment where then the next actual view call is going to be called has integrity, right, with respect to a given block. Right, and then here is sort of an example. The guest side of this is basically, you have two ways to actually do that, right? One is to use the sol macro of alloy that basically allows you to wrap into this sol just solidity code, right? So here we are looking at the very classical interface, the IRC20, the balance of, right? Basically, the only important thing about this is that it's a simpler, more human way to retrieve a function selector, which is basically this bunch of data that the EVM then needs to understand what code to execute. Practically speaking, we want to basically call the balance of a given account, right, and then get back some balance. Right, so as I mentioned before, right, what the guest does, it reads the input that are provided by the host, right, among this EVM input, which is basically this prepared environment that the host has provided with the help of some RPC, right, provider. And then in this case, we have the contract address that we want to query the balance, right, as well as the account of the the owner that we want to know the balance of, right? And then we literally just call the, sorry, important thing. The last line is actually where the magic happens, right? Which is basically making sure that the state, all this environment given by the host has integrity with respect to the committed root, right? And then you are sure that you are working on a safe, let's say, environment, and then you run this you call, right? And you get back some result, which in our case is the balance, right? So you can do whatever you want now. At this point, I was very imaginative and creative, so I decided let's check if this balance has at least one token, right? It's a pretty common scenario. And then you commit, committing to the journal. We call the journal basically the output, right, of running the execution, right, of the guest code. And we commit to the commitment, which is basically contains the the cryptographic insurance that the state was correct. So basically the root hash, right, and the block hash, and then the block number, I guess. Also, there are also other techniques, other way to commit using the beacon chain, but we can talk about that later. And then in this case, you also want to commit to the contract, right? Because otherwise you don't know who account you have. What contract you have used, right? It could be the my toy contract, right? So you want also to let the verifier know which contract has been queried. And that's basically it. Now, on the host side, instead, I already mentioned basically everything that is happening here, but I will just recap it. You just do some Alloy boilerplate shenanigans to get some provider. By the way, Alloy is super cool. Just say shenanigans too often. And then you basically create this environment, right? So basically you prepare the RPC node that needs to be used to do all this query. First of all, the real query that you are interested in, and then also use the same provider to get all the ETH get proof for everything you need. And then you actually run this pre-flight, which does what I just said. And then basically that's the input that you are gonna use to feed the guest. Now, once everything is done, you can use it on chain, right? Typically the terminology we use here just to help you understand what is happening here. The journal data is basically the output of the execution, right? And the seal is the proof. That's just call them like this. Right, so what you do, you decode your journal, and then you check whether the contract matches what you were expecting. And then you also validate commitment, meaning that in this case, you want to be sure that the state that you have used is actually a state that belongs to the chain or the chain, or it's the integrity of the claim, basically, against that chain. And then you verify the real proof, right? It's ZK proof. And then you are free to do everything you want, right? Like you can go crazy as much as increasing the counter, right? So I mentioned the commitment, right? That you need in order to make sure that you are using a valid state. And we currently support few techniques. The main two are either you use the block hash, so that you can on-chain use this opcode block hash, which basically give you access to the latest 256 older blocks, right? It's super easy and cheap to use. The drawback is that you only have access to, on Ethereum, basically the latest 50 minutes, right, of state, which might not be enough if your proof takes more time to generate, for instance, right? So a different approach then is using the beacon block root commitment, which basically comes from the the parent chain, the beacon chain, where long story short, in this case, assuming the chain that you're using supports this, you have 1 day, always 1 day. If you need more, there are mainly two techniques. One is to just refresh your proof, right? And the second is to deciding which block you want to commit at the beginning before generating the proof. Then you save that block to whatever contract, whatever state in the chain, and then you can take all the time you want. You can drink a coffee, you can go for a run, you can do whatever, right? And then once you are ready, you can submit the proof and then use that commitment because you have already saved it previously, right? Right. So, long story short, you can turn any computation into a very compact proof. We use RISC-16 to basically publish and verify the final proof on chain. And one good thing is that you can also, have different proofs and then aggregate them all together with a single RISC-16 proof. So the cost that you pay to verify a proof is not anymore the cost of, verifying RISC-16, which is basically pairing operation and some, elliptic multiplication, but it's basically a bunch of catch-up because it will be just a proof of inclusion against a root that is actually the RISC-16 proof. Right. Talking about something interesting. What can you actually achieve with this? Okay, imagine that, and when I say imagine, there are real applications that do this and even more. You need in your contract somewhere to run something like, I don't know, 500,000 or, in this case, 400,000 S-loads operation. That is something, right? It kind of consumes roughly 1.2 billion gas, which is equivalent as filling 30 blocks, which at this morning price, which is not even that crazy, it will cost you around $34,000-ish. But with still, you can achieve the same with under $10. It's, money is not, it's kind of relative, right? You might not care. I don't care, $10, 35,000, it's the same, right? But nonetheless, you get to do that in one single transaction rather than waiting, for 30 blocks and try to, outcompete all the other, people that want to write into some transaction in the same block. So even practically speaking, even if you don't care about money, it's super convenient, right? And then you get a proof that can be verified. The worst case, right, with the 300K of gas. In the best case, it's just aggregated, so it's a bunch of catch-up. And that is just one example. Then I'll let your imagination do the rest, right? I'll give you these useful links. We have a blog post here about boundless, and then we have this a recent announcement. When I'm talking about cool tooling, I also say production ready, meaning that the auditing phase has been already done. So what we are giving you is something that is reliable, right? To some extent, of course. Bugs are always out there. And then there is a recent published Steel Docs, which is super cool. There is like a little screenshot here. But yeah, you can copy these links and have fun with it. So that's basically it.